Hey
Hello,
everyone.
everybody.
Hello. So very nice song to start the day, right? Well, or to end the
Yes,
day, depends on where you are.
exactly. Now we are in a different time zone, so in a different time, so we can cover more people that we are following from different parts of the world. That's fantastic.
Yeah, I mean,
If the people want to suggest us any other song for the next webinar, we are open to it.
hmm,
The magnetic
it's a good
playlist.
idea. Um, I have to say, I suggested the one, so that's what I say. I like it. Very American song. Okay, how are you, Ellie and Emmy? How is the week going so far?
It's been a good week. We are preparing many things here, talking with many users, getting feedback from Frenetic AI, something that is important for us because we are co-creating this new experience. How about you, Ellie?
I think this is the very busy week. Uh, we are ready for APEC. All attendees that come to our booth are going to see the version free of Frenetic AI. I don't know if we can get an advance to attendees today. Maybe it's good.
Yes, I think that as a gift of all the people that is here at the end of maybe at the middle of the end, we can show a preview of what we are going to share there because we are gathering feedback. It's really important for you, for us to count with your feedback. So for all the attendees now, we are going to show a snack preview of what we are going to see there. So
Okay, fantastic. So if you stay until the end, it's only 22 minutes more. You will get the possibility to watch that and give your feedback. So
yes,
just thumbs up or thumbs down.
yes,
Okay.
we are building this together.
Okay. So should we start with
Let's
the
start.
real matter today? So as always, we will review a little bit the agenda. So just a brief review about what is the Frenetic simulator is our main business. Then we will work something also about the AI thing, or probably that would be at the end. I don't know. And then talking about the zero voltage switching, what is something that really is interesting today. So as you already know, our magnetic simulator is an online tool that will allow you to really get very accurate designs for your magnetics. Something that I would like to show today, always I share these kind of use cases, and here you have the QR code to request a demo or just go to our website. But something I'm going to show today here is also this. So this case, let me share again the screen. I'm finding this particular case very interesting. So this is a case of an LLC 130 bat where the predictions of temperature and the leakage inductance are extremely accurate. So in the measurements in the lab, we found 66 degrees and the temperature prediction of maximum was 65. But what was more interesting here is that we were able to build the waveframes extremely fast for the design. So the user were able to spend more time optimizing the core and the winding losses and getting this result because let's say the generation of the waveframes and the topology and all the power electronic support was extremely fast. So that was something very relevant to talk here today. So now I'm back to the presentation. If you know what you want, you can request a demo. Then talking a little bit about what is Frenetic AI. So you already know that we are working in adding more features in the part of the design of the converter. So just not on the magnetic, but also in the selection of the topology, looking for components. And this is the kind of part that is quite interesting. A lot of people is asking us, where are we using artificial intelligence? So this is a very good question, and I'm going to answer today. So we use artificial intelligence in 2 places. Right now, in the foil losses model that actually we will present at APEC, is a losses model for foil windings, and we use AI there. And the other model where the other use of AI is the LLMs that we use to interact with the users and with working with some text or data that is needed in the interaction. But we don't use AI for calculation. So when you are designing a circuit with us, that's not let's say that's not use AI. We have the equations and are very solid equations, so there is no kind of possibility of hallucination there. So the architecture of Frenetic AI is going to be something similar to what you can see now, is that there is a tool where you can manage a lot of tasks and activities, starting with a generation of LT-SPICE, designing power converters, or connecting with all the tools. So just to give you kind of, I think that you have access, most of you, to the first version of this technology, but just in case that you haven't seen, you can get access to Frenetic AI, that is this platform here. And let's use an example here to see for how this is working. And actually, we are going to use the same data. So 300 volts, 360 volts, and 2 kilowatt full bridge ratio. Then we will ask for the design. And we will come back to this point later, because this is going to design the converter, and we will need the converter design for the zero voltage switching conversation. So let's come back to the zero voltage switching. So last week we were talking about what is zero voltage switching. So you can review the recording where we discuss about, okay, zero voltage switching is very important for reducing the losses in bridge topologies like phase shift full bridge, and also the noise. So we explained the phenomena. So the phenomena occurs when you are switching in a leg between one MOSFET and the other. Usually, for avoiding short circuits, you don't have both switches on at the same time. Only in the current fed full bridge. In that case, yes, but not in most of the cases. So here, during the commutation between switching off M1 and switching on M2, this is this transition between the voltages here that can create a lot of kind of noise. In this case, it's an example where you can see that the MOSFET 2 switch on with zero voltage switching, because the voltage here in this node is 0. So what we are going to review today is a little bit more detail. So in this graph, we saw last week that this effect depends on the parasitic capacitance, leakage inductance, and the voltage. But now we are going to go to the source. So the source is this article from the Spanish guy, Juan Sabater. This article is from the 90s. Actually, it's from 1990. And that was when he was at Virginia Tech. This article, we're going to review the article, but I invite all of you to read the complete article. It's not very long, but it's basically it's the basics of the zero voltage switching for any full bridge application. I am going to end the review with an example of calculation. So let's start. So the first thing to talk about the zero voltage switching, once we understand that the zero voltage switching is the situation where you have to switch on an MOSFET, and if you have energy stored in that MOSFET, you are going to have losses. once we understand that, now we have to try to understand the when this is occurring and how to avoid that problem. So this is in this graph, you can see the current through the transformer. So you can see that this current is flowing through the transformer, and there are some effects that we need to verify. The first thing is that when these commutations are occurring. So if we check here the voltage applied to the transformer, we can see that there are some commutations occurring in this period, like in T4, but the main ones occur at T2 and at T5. The main thing here we have to understand is that during this period here, so let me take the pen. So here we are commuting Q1 and Q2. So when you are switching Q2, that it could be, let's say, a critical moment, what we have is maximum current here. So what that means is that the leg of Q1 and Q2 always have an advantage in terms of zero voltage switching, because they are occurring when you have peak current, and the energy here is the one that is going to help you to get zero voltage switching. So again, more current, easier zero voltage switching. So Q1 and Q2 in this commutation here, we are having some benefits. In the other side, when we have the commutation between Q3 and Q4, we have a different case that is different. Let's say Q2 and Q4. Yeah, the case is different because then that's occurring in different moments. Are occurring in different moments. So this is meaning that the current is not going to be in the peak. It's going to be in lower case. So for doing the calculations, always we have to consider the worst case. So the worst case is occurring for Q2 and Q4. So now let's move to the next point. So in this article, they explain very well how to calculate the worst case scenario. So the worst case scenario is to calculate what is the critical current through, let's say, in the primary side, where to achieve zero voltage switching. So this is the equation. In this equation, as you can see, the minimum current to achieve zero voltage switching, or let's say when you start having zero voltage switching, depends on the parasitic capacitance of the MOSFET, parasitic capacitance of the transformer, the square of the input voltage, and the leakage inductance. So this basically is saying that the energy in the leakage inductance needs to be higher than the energy stored in the parasitic capacitance of the MOSFETs plus the parasitic capacitance of the transformer. And in the next equation, what we are calculating is this peak. How much is this current? So this equation basically gives you a very specific instant of the commutation, how much energy you have stored in the leakage inductance. So it's like a very particular situation. And then once we understand that there is a critical value of current where we start having zero voltage switching, that means that if you are operating below, if your current in the primary is below this value, you won't have zero voltage switching. And that means that this is telling you in which range you are having zero voltage switching. That means that if you have a converter, like the one that we were putting an example of 2 kilowatt, this value will tell us in which moment we will stop having zero voltage switching. So you will have zero voltage switching always at higher, let's say, close to the maximum power, but in the lower values, is where you won't have. So this I critical will be somewhere here. And this is the value that we need to calculate. So let's move on. Now I'm going to do the sample. So let's do to the calculation, because this is going to be my last slide. So that would be for later. So here we have the design of this Coolbridge phase shift for this case. And we have a particular value of, let's say, magnetizing inductance and everything, but we will need to know which is the leakage inductance. Well, I'm going to ask the system to do that calculation. But in the meantime, I just built a small calculator here that is, I'm not a software engineer. So I just built this piece of Python to show to you the effects that we have seen before. What are those effects? So if you can see, can you see the numbers well?
Maybe it's a little bit small, but okay.
Can you see
yes,
the 600?
it's readable, yeah. Yeah.
Okay.
Yeah.
So
600.
these are the three parameters that we were talking before in the calculation. So I built a calculator that is going to say, okay, if you have input voltage at 600 volts and your parasitic capacitance is around, let's say, 82 picofarad, and your transformer parasitic capacitance is 100 picofarads, and I just run this, what I will have here in the output is that I have zero voltage switching starting at 745 watts. And for that, I will need a leakage inductance of 3.96 microhenries. If I, and this is going to be the way to understand this, if I decrease the value of the voltage, what do you think is going to happen? So what is going to happen is that we need less leakage inductance because the energy stored is going to be lower. And if, for example, coming back to the previous case, instead of that, what I increase is the, let's say, the parasitic capacitance, like crazy 10 times, I can see that I will multiply also almost by 10 and let's say the inductance need to have zero DC switching at the same level. If I want to change that, I need to choose that. So I fix that at 5 amps. So if I increase this number, probably I will be like increasing the range where I want to have, let's say, decreasing the range where I want to have zero voltage switching, but also changing the conditions. So I will need to play with that. But this is a calculator that probably will be very soon integrated in Frenetic simulator. So additionally to get in the magnetic design with the details of the leakage inductance and the output inductance, you will be able to know when your system is going to have zero voltage switching. And last point that was in my slide is that there is something also very relevant, that is the impact on the duty cycle. Why is that? So if we are going to this picture, it's going to be very, it's going to be very, very clear. So if you have a very high leakage inductance, it's not going to be for free, even if you are getting zero voltage switching and everything, but it's not going to be for free. So the taxes you are going to pay are going to be a decrement of the kind of conversion power of the transformer. So you can see here in the upper drawing here, the voltage that we are applying to the transformer. But this is the actual voltage you can see in the secondary. So this slope of that is dependent on the leakage inductance is going to reduce the effective duty cycle. That means that if you have an average value here of voltage, I don't know, like 10 volts, here you will get maybe 8 volts because you are losing some voltage. So you can see that the voltage that the cycle is shorter here than here. I think that it can be appreciated, right? So you also run, we don't have time today, but I ran some simulations with the circuit created with Frenetic. So this simulation basically is like, okay, I didn't put exactly the same numbers because I didn't have time. I did just this 10 minutes ago. But basically, you can see this is the blue line is the voltage in M4, and the green line is the voltage in the, let's say, the voltage. So this is the blue one is the gate driver of M4. And the green one is the voltage through the M4. So when you are switching on these, here we don't have zero voltage switching, because when we switch on, the voltage of this switch is almost at maximum value. That means that we will have here a peak of losses. And the effects here I'm going to show you is like if I increase the current, just moving to a higher range of current, like multiplying the current, let's say moving to a higher load. Let's see what's happened. So I run this simulation. So what I can see is that I'm improving. Still, there is no 100% of zero voltage switching, but you can see that now, instead of switching at maximum voltage, I'm moving this in this direction. If I continue incrementing the current or incrementing the leakage inductance or decreasing the capacitance, this will move here until I get maximum, let's say, or zero voltage switching. So I think that it has been very condensed 20 minutes. I hope that nobody gets too bored. But I didn't want to keep the people more time than we said at the beginning. If there is any questions, we can answer the questions. But as we promised, just in case somebody needs to leave, Emmy, do you want to show?
Yes, I will start already.
V3?
I will start sharing, and now you are seeing. Is it sharing? Yes, you are seeing the screen. Is correct?
Yeah.
Great.
We can see the screen.
Now,
Yes.
this is what we are about to build. Really is something that we are testing. We would like to have your insights. So please put your comments or react. This is what we intend to build. As you know, you have access to our first version, but we are building a final version. So what you're seeing as a preview of this is something that we build together. Well, we know that have many things on site, but we'll start for a project for power converters. And show here. And now what we have here is similar at the experience that you have access. So you can put your input voltage, output voltage, the power, and also the possibility to add more outputs. And additional details, this is open text that you can put, as also, as Chema mentioned, here is where you use the power of LLMs to translate all your requirements into the thing that we need. And here, for example, if we select a flyback, this experience allows to see the circuit here with the typical values of the magnetic inductance, output, and also the circuit parameters that you already see. And also, then we have, as you see, the LT spikes, and we can suggest the magnetic design. We put the losses, the total losses, the size, core, and winding. And also, you can open this in our simulator. So here, for this project, is where you can go deeper and make the fine tuning. We would like to see maybe with reactions and also with your comments, how is your reaction to this? So please feel free to have the reaction. For example, if you want to share, like it or something like that, feel free to share. We would like to see your insight, what you like, what you don't like about this. It's the best way to build it together. Any comments, or even if you want to share, we
Well, I think that there is a lot of comments, let's say comments, a lot of reaction. So thank
It's
you.
good.
I think that there are also a couple of questions.
Yes, for sure.
In the meantime, that the people please continue reacting if you want. Or let's say, giving us your opinion. In the meantime, we are going to start with the questions. Somebody is asking for the video of zero voltage switching 1. I think that now, Ellie, we can share in the next email after this event, let's say the 2 videos together, right?
Yeah,
like
yeah. Tomorrow we
1.
will share this recording, and together I will share with everybody the other video. So
Fantastic.
you will have the 2 parts together.
Okay. So Gregory has a big interesting question. He's saying like zero voltage switch is only for one switch of the leg. So no, actually, is for both. It's for those switches, both switches, and the only difference between one leg and the other is that in full bridge phase shift, the effect in one leg is, I mean, one leg is always easier to get zero voltage switching than the other. So you have to be careful with the worst case that usually is the second leg. That is what we call the lagging leg. The efficiency improvement is very relevant, especially for high voltage. The reason is that the losses are dependent on the, let's say, if you, let me share my screen for a second. So if you can see can you see the simulation, right?
Yes.
Okay, so if I add here the current, let me try current, then my friend, current, okay, I will do it manually. Traces. I and 4. Okay, then how do you call it? Transistor and 4. Well, I mean, what I want to explain here, I'm going to put the current maybe through this leg. So, okay, this is clear. So this current at this moment that this switch is off, is going to conduct this current. So when you switch off, what is going to happen in, let's say, when you switch on and there is voltage here, you will need to multiply this voltage here, exactly in this moment, by this current, and this is the area that will give you the losses. So here you can see that even at these cases, even with some partial zero voltage switching, we have 250 volts here, and we are going to multiply this for a few instants for almost 2 amps. That means a peak of 500 watt of losses during, let's say, a few nanoseconds. But the total energy to be dissipated in that chip maybe is going to be in the range of hundreds of milliwatts. So that's, let's say, the effect. So it's going to be, it could be very relevant. The point is that at maximum power, that is when you will have maximum currents, you have zero voltage switching without any problem. So the problem is usually at low loads, and that's the reason. There is another question from Gregory is, do you delay the switch through analog digital? Well, in this case, I mean, there is no delay. Let's say the delay for doing the phase shift. I would recommend always to use the chips from Texas Instruments, for example, UCC 28950, that basically do the control automatically, so you don't need to do any kind of digital thing. I have done digital thing, and basically at the end, you need to do like also the regulator, but the analog will work automatically perfectly. Sorry for the screen size. Somebody is just doing that. So I think that's all, no, for today.
Yeah,
don't worry. Don't worry for the screen side, because tomorrow in the recording we adjust the side screen for you.
Yeah, and in any case, if this is interesting for you, we will try to include the calculations in Frenetic AI, so then you can get the calculations there and play by yourself.
Yeah, great. Thank you a lot for being there. And well, next week we will be at the APEC, and the other week we will bring all the news from the APEC and continue with this.
Thank you very much.
Great.
Thanks a lot.
Thank you.
Have a nice
Bye
day.
bye.